Next topic we have in circles is called secants, tangents, and angle measures. This is just another way of looking at circles and lines that go through circles. A secant is a line that intersects a circle in exactly 2 points. So if we're looking at this, a line that intersects a circle in exactly 2 points. Sort of like a chord, except a chord ends at the circle. A secant goes on through the circle. And so we've got a drawing here. We have a circle. We have 2 lines. We have line AB. We have line CD. Line AB and line CD are both secants of this circle. Okay? Why? Because they intersect that circle in exactly 2 points. Now those secants do not have to go through any particular point at all, just as long as they go through the circle at exactly 2 points. So they're not tangents. Okay? They form chords. AB is a chord of the circle, and CD is a chord of the circle. Those segments are chords. The secants are lines that go on through and intersect that circle at exactly 2 points. Now the main theorem that we have with secants is this one. I call it the secant circle theorem, for no reason in particular. Secant circle theorem. If 2 secants intersect inside a circle, then the measure of an angle equals 1/2 of the sum of the arcs intercepted by the angle and its vertical angle. Okay, let's see if we can make any sense. If 2 secants, basically if 2 lines intersect inside a circle, those secants only, they're not tangents, they actually go through the circle, they intersected at 2 points, then the measure of an angle, any of the angles that are formed by that intersection, is 1/2 the sum of the arcs intercepted by the angle and its vertical angle. So if we're interested in angle 1, the measure of that angle is going to be 1/2 of the arc intercepted by that angle and the sum of the arc intercepted by its vertical angle. So basically we can add this arc, LP, and this arc, MN, together, divide by 2, and then we'll have angle 1. And we've got that right here. The measure of angle 1 equals 1/2 of the arc formed by angle 1 plus the arc formed by its vertical angle. Okay? So take the angle and its vertical, add the 2 arcs created by those angles, intersected by those angles, and divide by 2. So angle 2, using that formulation, then would be formed by 1/2 of the sum of the arc that it forms, LM, and the arc that its vertical angle form, NP. Add these 2 arcs together, take 1/2 of it, and that would be the measure of angle 2. Okay? So now we're beginning to look at ways that we can determine angle measures for which we couldn't make that out before. We couldn't calculate those things before. Okay, another theorem that we need to go over with secants and tangents, I call it the secant tangent theorem. If a secant and a tangent intersect at the point of tangency, what's the point of tangency? It's the point where the tangent intersects the circle. The one single point that the tangent touches or intersects that circle. So the point of tangency. If a secant and a tangent intersect at the point of tangency, then the measure of the angle equals 1/2 the measure of the intercepted arc. Now, there's actually 2 angles created here. Angle LZX is created, and angle MZX. Now, let's get that right, because I don't have that right over here. We need this as be X. Let's do that, yeah. That'll make that a lot better. Okay, so we have 2 angles, angle LZX and angle MZX are created. Now, what is the measure of those angles? Well, the measure of those angles are 1/2 of the arc that it intercepts. Well, what's the arc that's intercepted? Well, the arc that's intercepted here is xz, the minor arc xz. So therefore, this angle LZX is going to be 1/2 of that. Now let's look at the other angle, MZX. Okay, MZX is going to be 1/2 of the arc that is intercepted. Well, what's the arc that's intercepted? It's XYZ. It's the other portion of that, the rest of that 360-degree circle that's not included in this minor XZ arc. It is this major XZ arc, or XYZ. So therefore, this angle over here is going to be 1/2 of the arc XYZ. This angle here over this way is going to be 1/2 of the angle LZ. Okay? Basically, you can look at it as the same thing as the last, as the secant circle theorem. There we're adding the vertical arcs, the two vertical arcs that are created, and taking the average of those two arcs. Here we're taking the average of two arcs too. It's just that we don't have an arc over here. The arc over here is 0. The arc over here is 0. There's no arc there. So therefore we're adding this arc to 0 and taking the average. We're adding this arc to 0 and we're taking the average. Okay? So basically doing the same thing. It's just we don't have a vertical arc on this one. Okay, the last theorem we want to look at on secants and tangents, circles, is what I call the exterior secant tangent theorem. Basically, maybe call something else other places. If two secants, comma, a secant and a tangent, comma, or two tangents intersect in the exterior of a circle, in other words, outside the circle, then the measure of the angle formed is 1/2 the positive difference of the intercepted arcs. Let's see if we can break this down. Basically, it's looking at three different conditions. If two secants, what are secants? It looks like this right here. Okay, two secants, lines that come across the circle intersecting it at 2 points. Or a secant and a tangent, a line coming across intersecting at 2 points, and the line coming across it intersects at only 1 point on the outside of the circle, on the edge of the circle. Or two tangents intersect, two tangents, it would look like this, okay? Looks sort of like a snow cone effect. It just touches it at the very edge of that circle, okay? If they intersect on the exterior of the circle, in other words, if they come together and intersect, not inside, okay? We've already taken care of the inside, okay? It's not on the inside, it is exterior, okay? We've taken care of if they intersect on the inside or they intersect on the circle itself. Now we're looking at, does it intersect on the outside of the circle? It intersects on the outside of the circle. Then what we're going to do is we're going to take the two arcs that are formed on the circle and we're going to take the difference of those two. Okay? And 1/2 the difference. Alright? So let's look at this. If we have two secants, it looks like this. Angle A, the measure of angle A, is going to be 1/2 of the measure of arc CE. Okay? Arc CE, it is one of the arcs that's intercepted by those two secants. Subtract arc BD. So now we're looking at the difference of these two arcs that are created and then take 1/2 of that. Okay? The same thing happens here. Okay? We're going to take the difference between those two arcs that are created. Okay? And on all three of these, we're going to take the difference between the two arcs that are created. On here, we've got arc BD that is created. We're going to subtract arc BC from it and then take 1/2 of that. On the two tangents, we have a minor and a major arc. We're going to take the major arc, subtract the minor arc from it, and take 1/2 of it. The major arc is BDC, and we're going to subtract arc BC from it, and then take 1/2 of that. Okay, so we've got, this is our third theorem. We'll put up a little table that may help you a little bit here and explain that. Let's see if we can't make some sense out of these three theorems we've got here. If we have two secants and they intersect on the inside of the circle, then what we have is the measure of angle 1 is going to equal 1/2 of the measure of the two arcs created. This arc and this arc. That's all this is. If the intersection's on the inside, we're going to take half of the sum of the arcs created on the circle. Okay? If we're going this way, the arcs created here would be these two arcs. Alright? So, if the intersection of the secants is on the inside of the circle, then we're going to sum the two arcs and take half of it. If the intersection of the secant and tangent is on the circle, then we're just going to take 1/2 of the arc created, because there's only one arc created. In this case, angle 1 is going to be 1/2 of this arc BED. If we had an angle over here, it would be the arc BD. Okay? So what we're going to do, if it's on the circle, we're just going to take half of the arc created. Watch out for this one, it'll come back and bite you. Then, if the intersection is on the exterior, in other words, it's out here, it intersects outside of the circle, then what we're going to do is we're going to take the difference, the positive difference of the arcs created, and we're going to take half of that. So the measure of angle 1 here is we're going to take this arc, subtract this arc from it, and then take half of it. This one the same way. We're going to take this arc over here, subtract this arc from it, and take half of it. Over here the same way. We have three cases, or three situations, in which we can have an exterior intersection. Two secants, a secant and a tangent, and two tangents. Okay? Let's go over it one more time. If the intersection is inside of the circle, interior intersection, then we're going to take the sum of the arcs, take half of it, and that equals our angle. If the intersection is on the circle, then we just take the arc that's created and take half of it. Half of the arc created. Notice here, half the sum of the arcs created. Okay? Interior, the sum. On, half of it. Exterior, we're going to take the difference, the positive difference between the two. We're going to take half of the difference of the arcs created. Okay? All right. Trying to simplify that just a little bit, give you another way of looking at it. Obviously, take what works for you, flush the rest, and okay, because there's multiple ways for you to look at this. You know, look at this and study this enough so that you gain an insight for yourself and come up with a way that you can remember these theorems and how they work for secants and tangents and their intersections and circles.